What is the sun, really? The sun is a star. It's no different from lots of other stars, except that we happen to be near it, so it looks much bigger and brighter than the others. For the same reason, the sun, unlike any other star, feels hot, damages our eyes if we look straight at it, and burns our skin red if we stay out in it too long. It is not just a little bit nearer than any other star, it is vastly nearer. It is hard to grasp how far away the stars are, how big space is. Actually, it's more than hard. It's almost impossible. There's a lovely book called Earth Search by John Cassidy, which makes an attempt to grasp it using a scale model. 4 steps. Step 1. Go out into a big field with a football and plonk it down to represent the sun. Step 2. Then walk 25 meters away and drop a peppercorn to represent the Earth's size and its distance from the sun. Step 3. The moon, to the same scale, would be a pinhead, and it would be only 5 centimeters away from the peppercorn. Step 4. But the nearest other star, Proxima Centauri, to the same scale, would be another slightly smaller football located about, wait for it, 6,500 kilometers away. The distance between Oxford and New Delhi. There may or may not be planets orbiting Proxima Centauri, but there certainly are planets orbiting other stars, maybe most stars, and the distance between each star and its planets is usually small compared to the distance between the stars themselves. How stars work. The difference between a star, like the sun, and a planet, like Mars or Jupiter, is that stars are bright and hot, and we see them by their own light, whereas planets are relatively cold, and we see them only by reflected light from a nearby star, which they are orbiting. And that difference, in turn, results from the difference in size. Here's how. The larger any object is, the stronger the gravitational pull towards its center. Everything pulls everything by gravity. Even you and I exert a gravitational pull on each other. But the pull is too weak to notice unless at least one of the bodies concerned is large. The Earth is large, so we feel a strong pull towards it. And when we drop something, it falls downwards, that is, towards the center of the Earth. A star is much larger than a planet like Earth, so its gravitational pull is much stronger. The middle of a large star is under huge pressure because a gigantic gravitational force is pulling all the stuff in the star towards the center. And the greater the pressure inside a star, the hotter it gets. When the temperature gets really high, much hotter than you or I can possibly imagine, the star starts to behave like a sort of slow-acting hydrogen bomb, giving out huge quantities of heat and light, and we see it shining brightly in the night sky. The intense heat tends to make the star swell up like a balloon, but at the same time, gravity pulls it back in again. There is a balance between the outward push of the heat and the inward pull of gravity. The star acts as its own thermostat. The hotter it gets, the more it swells. And the bigger it gets, the less concentrated the mass of matter in the center becomes, so it cools down a bit. This means it starts to shrink again, and that heats it up again, and so on. I've told the story as though the star bounces in and out like a heart beating, but it isn't like that. Instead, it settles into an intermediate size, which keeps the star at just the right temperature to stay that way. I began by saying that the sun is just a star like many others, but actually there are lots of different kinds of stars, and they come in a great range of sizes. Our sun, below, is not very big as stars go. It is slightly bigger than Proxima Centauri, but much smaller than lots of other stars. What is the largest star we know? That depends on how you measure them. The star that measures the greatest distance across is called VY Canis Majoris. From side to side, diameter, it is 2,000 times the size of the sun, and the sun's diameter is 100 times that of the Earth. However, VY Canis Majoris is so wispy and light that, despite its huge size, its mass is only about 30 times that of the sun, instead of the billions of times it would be if its material were equally dense. Others, such as the Pistol star, and more recently discovered stars such as Eta Carinae and R136A1, not a very catchy name, are 100 times as massive as the sun, or even more. And the sun is more than 300,000 times the mass of the Earth, which means that the mass of Eta Carinae is 30 million times that of the Earth. If a giant star like R136A1 has planets, they must be very, very far away from it, or they would be instantly burned to vapor. Its gravity is so huge because of its vast mass that its planets could indeed be a very long way away and still be held in orbit around it. If there is such a planet and anybody lives on it, R136A1 would probably look about as big to them as our sun looks to us, because although it is much larger, it would also be much further away, just the right distance away, in fact, and just the right apparent size to sustain life. Otherwise, life wouldn't be there. The life story of a star. Actually, however, it is unlikely that there are any planets orbiting R136A1, let alone any life on them. The reason is that extremely large stars have a very short life. R136A1 is probably only about 1 million years old, which is less than 1,000th of the age of the sun so far. Not enough time for life to evolve. The sun is a smaller, more mainstream star, the kind of star that has a life story lasting billions of years, not just millions, during which it proceeds through a series of drawn-out stages, rather like a child growing up, becoming an adult, passing through middle age, eventually getting old and dying. Mainstream stars mostly consist of hydrogen, the simplest of all the elements. See Chapter 4. The slow-acting hydrogen bomb in the interior of a star converts hydrogen to helium, the second simplest element, something else named after the Greek sun god Helios, releasing a massive amount of energy in the form of heat, light, and other kinds of radiation. You remember I said that the size of a star is a balance between the outward push of heat and the inward pull of gravity? Well, this balance stays roughly the same, keeping the star simmering away for several billions of years until it starts to run out of fuel. What usually happens then is that the star collapses into itself under the unrestrained influence of gravity, at which point all hell breaks loose, if it's possible to imagine anything more hellish than the interior of a star already is. The life story of a star is too long for astronomers to see more than a tiny snapshot of it. Fortunately, as they scan the skies with their telescopes, astronomers can find a range of stars, each at a different stage of its development. Some infant stars caught in the act of being formed from clouds of gas and dust, as our sun was 4.5 billion years ago. Plenty of middle-aged stars like our sun, and some old and dying stars, which give a foretaste of what will happen to our sun in another few billion years' time. Astronomers have built up a rich zoo of stars of all different sizes and stages in their life cycles. Each member of the zoo shows what others used to be like or will be like. An ordinary star like our sun eventually runs out of hydrogen and, as I've just described, starts burning helium instead. I've put that in quotation marks because it isn't really burning, but doing something much hotter. At this stage, it is called a red giant. The sun will become a red giant in about 5 billion years' time, which means it is pretty much in the middle of its life cycle at the moment. Long before then, our poor little planet will have become much too hot to live on. In 2 billion years, the sun will be 15% brighter than it is now, which means that the Earth will be like Venus is today. Nobody could live on Venus. The temperature there is over 400 degrees Celsius. But 2 billion years is a pretty long time, and humans will almost certainly be extinct long before then, so that there will be nobody left to fry. Or maybe our technology will have advanced to the point where we can actually move the Earth out to a more comfortable orbit. Later, when the helium too runs out, the sun will mostly disappear in a cloud of dust and debris, leaving a tiny core called a white dwarf, which will cool and fade. Supernovas and stardust. The story ends differently for stars that are much bigger and hotter than our sun, like the giant stars we were just talking about. These monsters burn through their hydrogen much faster, and their hydrogen bomb nuclear furnaces go further than just banging hydrogen nuclei together to make helium nuclei. The hotter furnaces of larger stars go on to bang helium nuclei together to make even heavier elements, and so on until they have produced a wide range of heavier atoms. These heavier elements include carbon, nitrogen, oxygen, and iron, but so far nothing heavier than iron. Elements that are abundant on Earth and in all of us. After a relatively short time, a very large star like this eventually destroys itself in a gigantic explosion called a supernova, and it is in these explosions that elements heavier than iron are formed. What if Eta Carinae were to explode as a supernova tomorrow? That would be the mother of all explosions. But don't worry, we wouldn't know about it for another 8,000 years, which is how long it takes light to travel the vast distance between Eta Carinae and us, and nothing travels faster than light. What then if Eta Carinae exploded 8,000 years ago? Well, in that case, the light and other radiation from the explosion really could reach us any day now. The moment we see it, we'll know that Eta Carinae blew up 8,000 years ago. Only about 20 supernovas have been seen in recorded history. The great German scientist Johann Kepler saw one on 9 October 1604. The bottom picture on this page shows the remains of the explosion as we see them today. The debris has expanded since Kepler first saw it. The explosion itself actually occurred some 20,000 years earlier, roughly the time the Neanderthal people went extinct. Supernovas, unlike ordinary stars, can create elements even heavier than iron, lead for example, and uranium. The titanic explosion of a supernova scatters all the elements that the star and then the supernova have made, including the elements necessary for life, far and wide through space. Eventually, the clouds of dust, rich in heavy elements, will start the cycle again, condensing to make new stars and planets. That is where the matter in our planet came from, and that is why our planet contains the elements that are needed to make us, the carbon, nitrogen, oxygen, and so on. They come from the dust that remained after a long-gone supernova lit up the cosmos. That is the origin of the poetic phrase, "We are stardust." It is literally true. Without occasional but very rare supernova explosions, the elements necessary for life would not exist. Going round and round. It is a fact we cannot ignore that the Earth and all the Sun's other planets orbit their star in the same plane. What does that mean? Theoretically, you might think that the orbit of one planet could be tilted at any angle to any other. But that is not the way things are. It is as though there is an invisible flat disk in the sky with the Sun at the center, and all the planets are moving on that disk, just at different distances from the center. What's more, the planets all go round the Sun in the same direction. Why? It is probably because of how they began. Let's take the direction of spin first. The whole solar system, which means the Sun and the planets, began as a slow spinning cloud of gas and dust, probably the leftovers of a supernova explosion. Like almost every other free-floating object in the universe, the cloud was spinning on its own axis. And yes, you've guessed it, the direction of its spin was the same as the direction of the planets now orbiting the Sun. Now, why are all the planets on the level on that flat disk? For complicated gravitational reasons that I won't go into, but which scientists understand well, a big spinning cloud of gas and dust out in space tends to form itself into a revolving disk with a massive lump in the middle. And that is what seems to have happened with our solar system. Dust and gas and small chunks of matter don't stay as gas and dust. Gravitational attraction pulls them towards their neighbors in the way I described earlier in this chapter. They join forces with those neighbors and form larger lumps of matter. The larger a lump, the greater its gravitational pulling power. So, what happened in our spinning disk was that the larger lumps became even larger as they sucked in their smaller neighbors. By far, the largest lump became the Sun in the center. Other lumps, large enough to attract smaller lumps to them and far enough from the Sun not to be sucked into it, became the planets. Reading from nearest the Sun outwards, we now call them Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Old lists would put Pluto after Neptune, but nowadays it is regarded as too small to count as a planet. Asteroids and shooting stars. Under different circumstances, another planet could have formed too between the orbits of Mars and Jupiter. But the small bits that could otherwise have joined together to make this extra planet were prevented from doing so, probably by the brooding gravitational presence of Jupiter, and they have remained as an orbiting ring of debris called the asteroid belt. These asteroids swarm in a ring between the orbits of Mars and Jupiter, which is where the extra planet would have been if they had managed to get together. The famous rings around the planet Saturn are there for a similar reason. They could have condensed together to make another moon. Saturn already has 62 moons, so this would have been the 63rd. But they actually stayed separate as a ring of rocks and dust. In the asteroid belt, the Sun's equivalent of Saturn's rings, some of the bits of debris are large enough to be called planetesimals, sort of not quite planets. The largest of them, called Ceres, is nearly 1,000 kilometers across, large enough to be roughly spherical like a planet, but most of them are just misshapen rocks and bits of dust. They collide with each other from time to time like billiard balls, and sometimes one of them gets kicked out of the asteroid belt and may even come close to another planet such as Earth. We see them, quite commonly, burning in the upper atmosphere as shooting stars or meteors. Less commonly, a meteor may be large enough to survive the ordeal of passing through the atmosphere and actually make a crash landing. On 9 October 1992, a meteor broke up in the atmosphere and a fragment about the size of a large brick hit a car in Peekskill, New York State. A much larger meteor, the size of a house, exploded above Siberia on 30 June 1908, setting fire to large areas of forest. Scientists now have evidence that an even larger meteor hit Yucatan in what is now Central America 65 million years ago, causing a global disaster, which is probably what killed off the dinosaurs. It has been calculated that the energy released by this catastrophic collision was hundreds of times greater than would be released if all the nuclear weapons in the world were simultaneously exploded in Yucatan. There would have been shattering earthquakes, epic tsunamis, and worldwide forest fires, and a dense cloud of dust and smoke would have darkened the Earth's surface for years. This would have starved the plants, which need sunlight, and starved the animals, which need plants. The wonder is not that the dinosaurs died, but that our mammal ancestors survived. Perhaps a tiny population survived by hibernating underground. Light of our lives. I want to end this chapter by talking about the importance of the sun for life. We don't know whether there is life elsewhere in the universe. I'll discuss that question in a later chapter, but we do know that if there is life out there, it is almost certainly near a star. We can also say that if it is anything like our kind of life, at least, it will probably be on a planet about the same apparent distance from its star as we are from our sun. By apparent distance, I mean distance as perceived by the life form itself. The absolute distance could be very much greater, as we saw in the example of the supergiant star R136A1. But if the apparent distance were the same, their sun would look about the same size to them as ours does to us, which would mean that the amount of heat and light received from it would be about the same. Why does life have to be close to a star? Because all life needs energy, and the obvious source of energy is starlight. On Earth, plants gather sunlight and make its energy available to all other living creatures. Plants could be said to feed off sunlight. They need other things too, such as carbon dioxide from the air and water and minerals from the ground. But they get their energy from sunlight, and they use it to make sugars, which are a kind of fuel that drives everything else that they need to do. You can't make sugar without energy, and once you have sugar, you can then burn it to get the energy back out again. Though you never get all of the energy back, there is always some lost in the process. And when we say burn, that doesn't mean it goes up in smoke. Literally, burning it is only one way to release the energy in a fuel. There are more controlled ways to let the energy trickle out slowly and usefully. You can think of a green leaf as a low, spread out factory whose entire flat roof is one great solar panel, trapping sunlight and using it to drive the wheels of the assembly lines under the roof. That is why leaves are thin and flat, to give them a large surface area for sunlight to fall on. The end product of the factory is sugars of various kinds. These are then piped through the veins in the leaf to the rest of the plant, where they are used to make other things like starch, which is a more convenient way to store energy than sugar. Eventually, the energy is released from the starch or sugar to make all the other parts of the plant. When plants are eaten by herbivores, which means just that, plant eaters, such as antelopes or rabbits, the energy is passed to the herbivores, and again, some of it is lost in the process. The herbivores use it to build up their bodies and fuel their muscles as they go about their business. Their business includes, of course, grazing or browsing on lots more plants. The energy that powers the muscles of the herbivores as they walk and munch and fight and mate comes ultimately from the sun via plants. Then other animals, meat eaters or carnivores, come along and eat the herbivores. The energy is passed on yet again, and yet again some of it is lost in the transition, and it powers the muscles of the carnivores as they go about their business. In this case, their business includes hunting down yet more herbivores to eat, as well as all the other things they do, like mating and fighting and climbing trees and, in the case of mammals, making milk for their babies. Still, it is the sun that ultimately provides the energy, even though by now that energy has reached them by a very indirect route. And at every stage of that indirect route, a good fraction of the energy is lost as heat, which contributes to the useless task of heating up the rest of the universe. Other animals, parasites, feed on the living bodies of both herbivores and carnivores. Once again, the energy that powers the parasites comes ultimately from the sun, and once again, not all of it is used because some of it is wasted as heat. Finally, when anything dies, whether plant or herbivore or carnivore or parasite, it may be eaten by scavengers like burying beetles, or it may decay, eaten by bacteria and fungi, which are just a different kind of scavenger. Yet again, the energy from the sun is handed on, and yet again, some of it leaks away as heat. That's why compost heaps are hot. All the heat in a compost heap comes ultimately from the sun, trapped by leafy solar panels the year before. There are fascinating Australasian birds called megapodes that use the heat of a compost heap to incubate their eggs. Unlike other birds, which sit on their eggs and warm them with their body heat, megapodes build a big compost heap in which they lay their eggs. They regulate the temperature of the heap by piling more compost on the top to make it hotter, or removing compost to make it cooler. But all birds ultimately use solar energy to incubate their eggs, whether through their body heat or through a compost heap. Sometimes plants are not eaten but sink into peat bogs. Over centuries, they become compressed into layers of peat by new layers added above them. People in Western Ireland or the Scottish Isles dig up the peat and cut it into brick-sized chunks, which they burn as fuel to keep their houses warm in winter. Once again, it is trapped sunlight, in this case, trapped centuries earlier, whose energy is being released in the fires and cooking ranges of Galway and the Hebrides. dazzlingly bright, so comforting in cold climates, so mercilessly scorching in hot ones, it is no wonder many peoples have worshipped it as a god. Sun worship often goes together with moon worship, and the sun and the moon are frequently regarded as being of opposite sex. The Tiv tribe of Nigeria and other parts of West Africa believe the sun is the son of their high god Awando, and the moon is Awando's daughter. The Baratsi tribe of Southeast Africa think the sun is the moon's husband rather than her brother. Myths often treat the sun as male and the moon female, but it can be the other way around. In the Japanese Shinto religion, the sun is the goddess Amaterasu. Under the right conditions and over millions of years, peat can become compacted and transformed so that it eventually becomes coal. Weight for weight, coal is a more efficient fuel than peat and burns at a much higher temperature, and it was coal fires and furnaces that powered the Industrial Revolution of the 18th and 19th centuries. The intense heat of a steel mill or a blast furnace, the glowing fireboxes that sent the Victorian steam engines thundering along iron rails or their ships pounding through the sea, all that heat came originally from the sun via the green leaves of plants that lived 300 million years ago. Some of the dark satanic mills of the Industrial Revolution were driven by steam power, but many of the earlier cotton mills were powered by water wheels. The mill was built near a fast-running river, which was ducted to flow over a wheel. This water wheel turned a great axle or drive shaft, which ran the length of the factory. All along the drive shaft, belts and cogwheels drove the various spinning machines and carding machines and looms. Even those machines were ultimately driven by the sun. Here's how. The water wheels were driven by water, being pulled downhill by gravity. But that works only because there is a continuous supply of water up on the high ground from where it can run downhill. That water is supplied in the form of rain from clouds falling on the hills and mountains. And the clouds get their water through the evaporation of seas, lakes, rivers, and puddles on earth. Evaporation requires energy, and that energy comes from the sun. So ultimately, the energy that drove the water wheels that turned the belts and cogwheels of the spinning machines and looms all came from the sun. Later, cotton mills were driven by coal-fired steam engines, again using energy ultimately from the sun. But before they switched to steam entirely, the factories went through an intermediate stage. They kept the great water wheel to drive the looms and shuttles, but used a steam engine to pump water up into a tank from which it flowed down over the water wheel, only to be pumped back up again. So, whether the water is raised by the sun into the clouds, or whether it is raised by a coal-fired steam engine into a tank, the energy still comes from the sun in the first place. The difference is that the steam engine is driven by sunlight collected by plants millions of years ago and stored underground in coal, whereas the water wheel on a river is driven by sunlight from only a few weeks ago and stored in the form of the water up at the top of the hills. This kind of stored sunlight is called potential energy because the water has the potential, the power within it, to do work as it flows downhill. This gives us a nice way to understand how life is powered by the sun. When plants use sunlight to make sugar, it is like pumping water uphill or into a tank on a factory roof. When plants, or the herbivores that eat the plants, or the carnivores that eat the herbivores, use the sugar, or the starch that's made from the sugar, or the meat that's made from the starch, we can think of the sugar as being burned. slow burned to drive muscles, for instance, just as coal is fast burned to make steam to propel a drive shaft in a factory. It wouldn't do us any good if we literally burned our sugar and other food fuels by setting fire to them. Burning is a wasteful and destructive way to recover the sun's stored energy. What happens in our cells is so slow and carefully regulated that it is like water trickling down a hill and driving a series of water wheels. The sun-powered chemical reaction that goes on in green leaves to make sugar is doing the equivalent of pumping water uphill. The chemical reactions in animal and plant cells that use energy to drive muscles, for example, get the energy in carefully controlled stages, step by step. The high-energy fuels, sugars, or whatever they are coaxed into releasing their energy in stages down through a cascade of chemical reactions, each one feeding into the next like a stream tumbling down a series of small waterfalls, turning one small water wheel after another. Whatever the details, all the water wheels and cogs and drive shafts of life are ultimately powered by the sun. Perhaps those ancient peoples would have worshipped the sun even more devotedly if they had realized just how much all life depended on it. What I now wonder is how many other stars drive engines of life on their own orbiting planets. But that must wait for a later chapter.